Okay, what's next? Let's see. So I'll comment this out and then reload, and we see that after cut comes paste. So we now have a notion of cutting things up, right? But eventually we also want to paste things back together because we have our windows in different pieces and we want to make them into one big window. So here's the appropriate notion for that. Pasting for a given notion of cut and some x is a way to take a cut up x, that's what this means, right? The meaning of the cut applied to x, and put it back together into a single x again. Right? So if you do this exercise, it's going to become much clearer about what I'm talking about. So here we're saying that we can take a nut cut of vectors and put it back together into one vector again. At least if you look in the library. So after this, I have given you this slightly complicated thing because that's only fair, because you have given me all the pieces that you need to make it. And what does it say? Well, it says that if we have two notions of cut for different dimensions, and if we can paste in each separate dimension, so I can paste for F according to C, and I can paste for G according to D, then I can paste for the combined cut in both dimensions. So this is how we're cutting rectangles, for example, right? And then we can paste for G composed with F. But in order for this to work, then we really need G to be applicative. So that's why we built the all yank function earlier, so we could yank the G out, etc. So I've given that to you, but your task is to actually deploy it here and see how we can, in particular, paste for rectangles and for matrices, where a matrix is defined to be a vector of vectors, just like you remember from Coursework 1, right? And then you can in turn use this pasting in order to make a many-cut of rectangles into a matrix, again using things that you've done before possibly. And after that, we're going to take a short break from all the crazy stuff and consider something a little bit more down to earth, which is how to lift relations pointwise to lists. So this is just about lists again. And before we had a way of listing a predicate pointwise to a list, right? If I had P from A to Z, then all of P was from list of A to Z. And here similarly, we have the same thing, but not for a predicate, but for a relation between two different types, X and Y. And then we're lifting that to a relation between lists by asking for this relation to hold for every pair of elements in the list. So we're saying this by saying that for the empty lists, they are trivially related pointwise because there are no elements. And if I have two non-empty lists, then I want the heads to be related, and recursively I want all of the tails to be related. Right? And then you can show that this is reflexive. So X is always related to itself for the equality relation in particular. And it also has the notion of a map function. So if R implies S, where you have to do the right thing with some extra functions, which in general they go from A to C and from B to D. So if R implies S, where we have to use the F and the G to transform the A into something that type checks, then pointwise of R implies pointwise of S. And now we have to map with these functions for the types to make sense. So this quite often happens that this pointwise refers to lists, so it makes sense that the map function for pointwise refers to the map functions for lists. Okay, so that's a little bit of relief in the middle of the storm perhaps, and then we go back to cutting things up again.